Hello everyone. I can't introduce myself any better than Aaron just did. So this is my talk. It's implications of interoperability. I just want to talk about what it actually means to have an interoperable network of chains. Like if you have all these chains that do specific things, what can you actually get out of that? What does it mean to you, perhaps as a developer, as a builder, as someone who wants to put things together on the chain level or perhaps at the application level? Just what sorts of things are possible. But first I would start with sort of a guiding principle that has really been the driving force behind a lot of the work that we've done over the last couple of years. This idea that specialization breeds optimization. You know, if you give developers more flexibility, if you don't lock people into a specific framework or a specific way of doing things, that they can have a lot more freedom. And that applies not just at the step of building things, but also at the stage of computation of data formats, that we want to unlock as much algorithmic potential as possible, that you can really get the best theoretical performance and get the most out of what you're doing. And specialization breeds optimization is just a nice way of putting that sentiment. So what we've seen so far is that one size doesn't fit all. Like if you try to build basically any application on a blockchain right now, you're going to run into huge scaling issues. You're going to run into issues with storing your data exactly right. The ways that blockchains give you to construct applications are not sufficient. If you try to build something like a prediction market system, you're going to want to store order books or things like that on-chain in ways that current smart contract platforms just don't give you the flexibility to do. So we need a way that allows you to specialize. So the current blockchain system is a bit like this group of bubbles floating around. They don't interact really. If they bump into each other, they're likely to pop. They try to do everything and be everything to every application. That doesn't really make much sense. If you instead created a network where the bubbles were heterogeneous and that they did specific things very well but could interoperate and could just pass messages, relay the notion that work should be done on one chain for a period of time, some computation, some file should be stored, then that would be a much more powerful paradigm. So we're facing this very fragmented landscape where every blockchain is trying to be a smart contract platform and a currency and a scalability solution and have a new consensus algorithm, etc. But they can't even talk to each other. They have to go through centralized services. This kind of defeats the purpose of blockchains in the first place. We want to be able to decentralize. We want to be able to have provable security under specific network assumptions and things like that. We don't want people to be locked into a specific platform. If I talk for a second about what a blockchain is actually composed of, there are two key parts. So the first part is the one that gets talked about a lot, but actually, to be honest, from a builder or user's perspective, doesn't actually have that much significance or importance. And that's the consensus algorithm. So consensus is just a way of agreeing upon what changes have been made, in which order, and getting sort of this universal agreement on that. So the issue with consensus is not to agree that some payments have been made, it's to agree that they happened in a specific order. And we can use something like proof of work or proof of stake to provide economic incentives for that. But what you usually get when you're building a blockchain, what you usually care about is what we call the state machine. So those are the changes that the consensus algorithm actually agrees upon. Whether it's a smart contract platform or a currency, or if it negotiates file storage or does oracles or things like that, that's the unique thing that as a builder, you have this idea and you're trying to put together when you build a chain. You're not usually thinking about exactly how you secure it because, the important implications come after security. So if we were to talk about deduplicating labor, a good start would be to make it so that not everybody who's building a blockchain is building their own, implementing their consensus algorithm. I mean, whether or not they invent it from scratch, they still have to put in the work to write something, right? until, and I'm sure a lot of you saw Gav's talk yesterday about Substrate, until Substrate, there wasn't really a convenient way to just sort of take some consensus algorithm somebody had written and then throw the meat of a blockchain onto it, that actual thing that you're trying to do. So one big aspect of our goal is to reduce friction for builders. That they can sort of just take this bundle of libraries like Parity Substrate and get out consensus and get out networking and get out synchronization and the database and all of that and just come away with more or less a complete blockchain. The only thing that they would be writing would be that state machine. So if we talk about guiding design principles in an interoperability framework, we would want, firstly, hierarchicality. So this idea that you can have chains nested within chains, that messages can be passed all the way up and all the way down, that it's basically something that can grow infinitely, that it can be extensible with basically any new protocol or algorithm that's been conceived of. We do this through the use of something like Turing-complete computation. If you have a system that's extensible, that means that you don't have to worry about the technologies you're using right now, that you can support the past, the present, and the future. You can support what's already been thought of. You can support basically the limits of what people are thinking of right now, and then as new research comes to light, you can also extend the system to support stuff that hasn't even been thought of yet. So that's the main goal of extensibility. Developability is a huge one. This idea that developers can actually build something with it rather than having to spend months and months duplicating the efforts that others have already done. Of course, scalability, this is something to go into in an entire other talk. We are running into these issues, but an interoperability framework does need to be scalable. Like right now, you would run into, at the root level, quadratic scaling issues. Simply because if you have a bunch of chains and you have a message queue from every chain to every other chain, that's a quadratic amount. So that's a fundamental scaling issue. But if you have this hierarchicality of chains, you can sort of limit that, where by localizing chains close to each other to the ones that they need to speak to the most, you sort of reduce this scaling barrier, that you can compress many chains communicating into what seems like one chain communicating with others. So that sort of notion of locality is useful not just at the chain level, but also at the application level. And I'll get into that a bit later, how that's important from an interoperability perspective. And lastly, of course, we want it to be extremely general, that we don't lock developers into or users into any specific constraints about exactly how their data is stored, exactly how you meter for computation. The coarser the grains of computation that you meter for with fees, the more work you can basically do. Like if you have to stop every single instruction and charge a fee, you're going to end up doing half as much work as you would if you have much coarser operations like store a kilobyte. So what blockchain interoperability is in a nutshell is that chains are initially isolated and serve a distinct purpose, that they're basically useless on their own, that they might not even have like a backing currency or something that really properly provides incentives. But then you connect them with this messaging framework, this idea that blockchains can then issue some kind of event that leads to a new extrinsic or transaction being applied on another chain. And this is done in a predictable way, that those messages that are passed have a predictable set of rules that, if you send message A before message B, that message A is always going to arrive before message B. And another very useful property that you would want is that message A is guaranteed to arrive. That way you don't have to deal with things like acknowledgements and receipts as much. Those are still useful for applications, but they don't become a prerequisite for any messaging, which means that if your messaging system guarantees that messages will actually be delivered, then you can already get started with, without having to deal with as many assumptions. So I mean, if we think about a pretty simple way to do this, it would seem that the way to do it is just have every chain, come up with some kind of bridge, and connect them all with a bridge, right? So you have a bridge from every chain to every other chain. But the challenge this runs into is attacking weak chains. So the truth is that everything has a price. I mean, people will talk in consensus about absolute finality and things like that, but it's not really absolute finality. There is some amount of stake which has been put on the system in the case of mining, which doesn't have absolute finality. There's some amount of dollar cost GPU or ASIC power that's being thrown at that chain. So finality can always be reverted for a price. Absolute finality really just means we have reached the price threshold. And that's what consensus algorithms try to do, is bring that price threshold to revert a block up to the maximum immediately. So if you took that approach with bridges, and you have one chain that's fairly weak in security and one chain that's stronger in security relatively. Let's say this green block is finalized on the weaker chain and sends a message to a block on the second chain. But if that first chain is attacked and the green block no longer exists in the finalized chain, then you might have a message outcome existing on the second chain, whereas the cause doesn't exist on the first chain anymore. And that's basically a double spend. But if you get into transitivity and things like that, it can cause really serious problems. So one major goal of an interoperability framework is to really protect against this property, that you want attacking one chain to be as expensive as attacking all the chains, sort of uniting them under a single source of security. And that's basically what Polkadot does. So I've talked in other talks, the deep dive on, what Polkadot does, exactly how it works from an economic standpoint, what it means to developers. So I won't go into all of that now. There are other talks for that, and you can always find me after, and we can chat about that. In this talk, I really just wanted to stress what it actually means to have this network of interoperable chains. So the way that Polkadot works in this sense is that you have a relay chain which negotiates the passing of messages between many other chains. And it unites them all under a single consensus process. It also unites this hidden state of all their message queues underneath that consensus process. So that's Polkadot in a nutshell. Now, that actually turns out also to be a very useful tool for scalability. So that's not initially the goal of interoperability, but it turns out that this solution to the interoperability problem also plays very nicely with scalability, because then you can get things like hierarchical chains and forms of sharding very easily under that same model of uniting distinct and heterogeneous state transitions under the same consensus process. So the last section of this talk, I would go into basically interoperability on the application level. So, of course, if we think about Polkadot or an interoperability framework sort of as infrastructure for infrastructure, the main things that are going to be delivered initially are going to be pieces of infrastructure, those chains that do specific things that aren't particularly useful on their own, but then when brought together can actually leverage a huge amount of applications. So, of course, those are going to be sort of the first things that you see appear. You're going to see chains about file storage, about oracles, smart contract platforms still, for scalability, for state channels, and that sort of thing. But then you really want to understand, okay, like how do I actually build upon that? What do the paradigms sort of look like? So I think this forest is a pretty good visual metaphor for that. Like, we have these trees, they can't really move. I'm pretty sure they can't move. But they sort of serve their own distinct purpose. Like, they're grounded, they're strong, but this deer can move among them and sort of, feed on like the leaves that have fallen off of each and every one of them, and the deer is basically the application in the sense that it sort of unites them, that it brings the forest together, and that the forest is greater than the whole. So again, to speak about locality. So the cost of sending messages asynchronously between chains is likely to be not tiny. So what that means is that if you have an application that needs to speak to something like a decentralized exchange or a specific parachain in the system, that it should be as close to that as possible. And one way you could even think about that is having modules for things like smart contracts embedded into those those specific purpose chains as just a small component, so that you could have proxy contracts and things that sort of store some of that state as close to that as possible. That you would have synchronous communication within that chain, and you try to move some portions of your application to live within that chain if possible. So if we speak about asynchronous and synchronous communication, asynchronous basically means that you don't get a response immediately. Synchronous means that you will send a message and get a response immediately. So what that sort of manifests itself as is something like the current smart contract paradigm, where you make a subcall to another smart contract and it waits and it gets a result. Or if the inner call throws, that the entire transaction is thrown. So with asynchronous communication, it's not like that. It's more like you just send the message out into the void, and you know that it's going to arrive, and in some future transaction, you might get a receipt, you might not, you might have to deal with timeouts and things like that. It's a bit more complicated to think about. Ultimately, it is a more powerful primitive. It means that you can do a lot of more things in parallel. It means that you can advance chains without blocking. It's ultimately more powerful, but you do gain some developer overhead by using asynchronous communication. So what that means is that as an application developer, you would try to minimize the amount of asynchronous calls in favor of using synchronous calls within chains, that you try to localize some kind of logic that ties many chains together within a single chain. So this chain would have an application deployed upon it that sort of negotiates between all the others and does synchronous work internally and farms out using asynchronous calls to do external work in the background. So one example of this would be something like decentralized exchange. So one implication of tokenization is that unlike traditional transfers of value, you can have behavior integrated into the transfer of a token, right? So like if you were to write something like a Solidity smart contract right now, that you could, in the transfer function, add some new kind of behavior. That's not really possible, like with example, bearer bonds or bearer bills or things like that. So what that means is using the original contract infrastructure when you're doing something like decentralized exchange is very valuable. But if you have these contracts living on many chains, that this has to use asynchronous calls to deal with them. This is just one approach to the DEX problem. There are like many different approaches with different trade-offs in the interoperability space. So let's imagine that DEX also wants users to be able to trade directly from their wallets, which means users wouldn't be locking up their funds, that they don't have to transfer them specifically to some chain and they don't have access to them, but rather they can post orders, even though their wallet is on a completely other chain, technically. That their balance is stored and not locked up on another chain, that they can still make orders. So what this would sort of look like if you use the DEX chain for escrow is that the DEX can send this attempt transfer call to token contracts, or what appears to be token contracts. We don't know if they're actually token contracts. They just follow this same messaging protocol. So these two tokens, token A and token B, live on different chains. And they are sort of wrapped in this thing that can take an attempt transfer call. So that attempts to transfer the money out. It might have been moved in the meantime because it's not locked. So what happens then is, if they're both successful, we get this message back into the DEX that says, okay, the money has been escrowed, it's sort of in the custody of the DEX parachain account. And then from there, the DEX can continue on and do the swap. If one of them fails, the DEX can then pass back the funds to the original owner of the other token. So that's one approach how this might look in a interoperable system. One other option would be something like adding a DEX module to every chain that might need it. And if you use something like Substrate, you would have these little runtime modules that are pretty easy to hook together. So you would just go on GitHub or on some kind of central module repository while you build your chain. You say, OK, I'm going to drag in the DEX module and put it in my code base and sort of link it together with the specific thing that I'm doing. Like if I have a token that accomplishes a specific incentive mechanism in my chain, that I can then link this into the DEX thing, and a little bit of trading will happen on my chain, whereas my chain will be mostly specialized for this specific task. And then you would have something like market makers balancing reserves among them in the background. So you would have all these different DEX modules living on different chains with market makers sort of moving money behind the scenes with asynchronous calls. And that's good because the asynchronous calls don't have to happen that often. They only happen for large transfers of value. But of course, we aren't just talking about tokens. When we speak about an interoperability framework, we're thinking beyond tokens. So tokens have proved so far to be a very useful way of dealing with value in a decentralized system. When you're programming a blockchain, that tokens can encapsulate a lot of different kinds of value. But at the same time, we are looking at a system that can transfer arbitrary messages. So arbitrary messages being a superset of just transferring tokens, you can transfer tokens using arbitrary messaging, but you can't do arbitrary messaging using just tokens. So general smart contracts still have a place. And the reason for this is that smart contracts are essentially specialized for interoperability, that you can do. That's intraoperability, not interoperability. So you can do communication within a smart contract platform synchronously and very efficiently. It's basically optimized for maximizing the network effect within a specific bubble. And that means that if you have a lot of moving parts that are very distinct, that they can still interact under a chain that's specialized for that. Whereas if you have chains that are specialized for other work, that they can also interact with those in an albeit slower method. So what a cross-chain smart contract call would look like would be pretty simple, and the slide also details one possible use case of that. So a cross-chain smart contract call is basically a message comes from one chain, and it's received on the other, and the smart contract chain can interpret that message as, it looks at the bytes, it looks at the format. If it's good in the format that it expects, it continues to process it. This format that it expects would probably be something like a address of the contract to call, data to call it with, and a fee that covers the cost of computation, right? And you could even fund the sending of a receiving of a receipt or acknowledgement message within that initial call. But let's imagine that you have something like a storage provider chain, which is funded and programmed. The only thing it knows how to do is every time an event happens for a specific file that's stored is to send a message, some message that's been pre-programmed by whoever stored the file, to some chain. So you could do this with a smart contract. You could have the file storage chain, whenever the state of the custody of that file is updated, send this message to the smart contract, and the smart contract could then refund that custody. Or when that file, for some reason goes down, when the contract is no longer funded, that it can roll out a mitigation strategy for, okay, what happens when this data that we've hash committed to is no longer available. And one other example I would use is something like an IoT chain. So we've seen that so far one of the biggest barriers to adoption to the stuff that we're building these days is that it's actually pretty heavy to use. So like even if you use a light client on Ethereum, you're probably going to be using, at the very least, something with a strong Wi-Fi connection. So if we want this stuff to actually be used, you need to make it available to stuff that doesn't have really good internet connectivity. Like computation and memory are also not great on light clients, but bandwidth is really the key. So if we talk about something like IoT devices on LoRaWAN, low frequency radio, that can only receive a few kilobytes of data per day, then something like an existing light client is not going to be enough for them. So imagine if we had an IoT chain, which is basically, this is one kind of IoT chain, but this is an IoT chain which is basically just a record of messages received that are kept in the state. So IoT devices that are listening can get consensus proofs, which are fairly cheap, of finality of a specific block, and then get cheap Merkle proofs of some messages that were received, some notifications that happened. And those notifications could have come from any other chain in the system. And you could also have a transaction that you can broadcast to this chain that simply triggers message to another chain. So what this does is it basically opens up the entire network of chains, which might do complex computation and have complex state, to something like a very low bandwidth IoT device. And that would probably be really powerful. It means that you could have something sitting in your fridge or in your light bulbs. I mean, whether you want that exactly is up to you. But it's possible that you could have these very low bandwidth devices that listen for events from this huge network of chains that are doing a lot of work and still be able to securely see that computation has been done and to farm it out themselves. It's not something that's been possible so far. And with that, I'll conclude it and take a couple questions. So thank you very much.
Rob, thank you very much for that. Rob Habermeier, ladies and gentlemen. We've got a bit of time for a question before the next session.
Hi there. How's it going? Something Gavin talked briefly about yesterday was upgradability, which is a problem that many smart contract platforms have right now. I was wondering if you could expand upon that a little bit into, maybe briefly high-level overview of what an architectural pattern for contract upgradability and blockchain upgradability would look like in the Polkadot ecosystem.
Yeah, so when we speak about blockchain upgradability, there's basically two paths towards it. One is that if we speak about actually how a blockchain is encoded in the system, it would be encoded as a representation of its state transition function. So the actual work that's being done is expressed as code and put into the system. It's registered on-chain on that root level relay chain. So one thing you could do is actually have the chain issue some kind of special message that says, upgrade my code, right? And then it could be upgraded. The other alternative is to register a new chain that has the new code and sort of hard fork that community without hard forking, that they're both connected and that the community knows that, okay, we're going to migrate things over to the new one, but it hasn't actually deregistered the old one. And that's kind of cool because you don't get into this schism situation where it's either one or the other, that both are still deployed and one can be slowly phased out.
Cool. We'll start to need to move on to the next session, which will be a panel discussion. So if anyone else wants to talk to Rob, then he'll be moving on out to the AMA corner. But right now, please put your hands together again for Robert Habermeier. Thank you.